The mean value theorem states that between any 2 points, if it follows the condition of smooth and continuous, there must exist a tangent point that is the same slope as the average slope. Okay, so the condition really is smooth and continuous. So this is smooth and continuous, so we can apply the mean value theorem between these 2 points, because there must exist some point in between these 2 coordinates that has a parallel slope, which is true. Okay, so here, this is not smooth and continuous at that point. So if I try to apply the mean value theorem, there's my average slope between the endpoints, and nowhere on the graph is there a parallel slope because it does not establish smooth and continuous. Okay, so it fails here. So we have to eliminate that one. And the same thing here, there's a kink here. So as we try to apply the mean value theorem, there's my average slope, and nowhere in this interval is the slope equal to the average slope. Okay, and again, the reason is because of this point of not discontinuity, but this point where it's not smooth and continuous, where it's not differentiable. So this one fails that one as well. So the only one that we can apply mean value theorem of smooth and continuous is that one there. For here, which is for what values of the function differentiable? Well, if we have x is less than -1, it's differentiable. At -1, there's no derivative. Between -1 and 1, and not at the endpoints of -1 and 1, it is differentiable. Okay, so there's another point. Between 1 and 2, okay, it again is differentiable. And from 2 to infinity, we'll assume that's going on, so x is greater than 2, and again, not at the endpoints, because again, endpoints are not differentiable. So in all those intervals, we can say that it is differentiable. We could also write it like this, -infinity to -1, okay, from -1 to 1, from 1 to 2, and from 2 to infinity. We can write those intervals as well in interval notation. Okay, so lastly, for the function, f of x equals e to the x 3 times 3 sine x plus 1. How can we use IVT to show a solution to the equation 0 equals e to the x 3 sine x plus 1 exists between pi over 2 and 3 pi over 2? Well, first of all, the IVT needs a condition. It is continuous. Okay, so f of x is continuous on this interval. Okay, we know this is the case because there's no denominator restrictions here. We know that e to the x is continuous on that interval. We also know that sine x is continuous on that interval. So first of all, we've met the condition. Okay, so we have our condition. Okay, and I'm going to test the endpoints here, the endpoints of the boundaries. So f of pi over 2. When I work that out, I'm going to end up with e to the pi over 2, which is positive. Sine of pi over 2 is 1, so we get 4 times that, okay, so which is positive. And really this is what I'm looking for. I'm looking for if it's positive and negative because I know in between positive and negative exists a 0. So if I do f of 3 pi over 2, I get e to the 3 pi over 2. Okay, plug in 3 pi over 2, that's going to be -1. So I end up with -2. This is -2 e to the 3 pi over 2. Well, 3 pi over 2 is always positive. So this is a negative value. So I know that at pi over 2, I have some positive coordinate. At 3 pi over 2, I have some negative coordinate. And I know that since this is continuous, there is at least one zero. There could be more. I mean, it could look like this. We don't know. But I know that at least there between these two intervals, these two values, there's at least one point where it equals 0. So I know that since fx is continuous, there's my first point of my argument. The second point of my argument is that the endpoints are opposite signs. So my conclusion then is that by IVT, okay, intermediate value theorem, there exists a 0 between pi over 2 and 3 pi over 2. Okay, in that interval, and I'm writing it in interval notation.